السلام عليكم. اوكي. Already.
صار في مجال أسأل سؤال.
تفضلي. يا
دكتور لما حكينا نستخدم stationary reference frame أو rotating أو synchronous، احنا بنوصف حركة الروتور صح؟
No. The reference frame.
لما نحكي stationary reference frame يعني إيش يعني؟
This means that the reference frame is attached to the stator, which means that the reference frame is not rotating.
اللي هو الروتور؟
No. The reference frame. I'm assuming a virtual frame. Just a minute. In general, in the induction machine or later on in any machine, I'm having stator and rotor. This is AS for the stator. And here I'm assuming three-phase system. This will be the BS and this will be the CS. And also we have a rotor frame that's rotating by the rotor speed. So let's assume that this is AR. This is the BR. And let's assume this is the CR. Now, the frame of the rotor is rotating by which speed? By the rotor speed. Huh? This is the AR, and here we are rotating by omega r. Now, in the reference frame theory, I'm having a 2x, let's say, a 2x. So let's assume that this is the QX, and I'm having 90 degree over this one, and this will be the DX, correct? Now this frame is rotating by which speed? By omega speed, arbitrary reference frame. Now, if omega equal to 0, this means that this frame is stationary, is never rotate. Yes?
Yes.
If this frame, if omega is equal to omega E or omega, then this frame is rotating by which speed? By the synchronous speed. Yeah?
Yes.
Which is 2 by F. Huh? Now, if this frame is rotating by a speed which is omega r, then this frame rotating by which speed? By rotor speed. Yes. So the reference frame is seen to be attached to where? To the rotor. Seen to be attached to the rotor. Yes. Now, the D and the Q, those are not actual frame, virtual frame. Yeah. In the same fashion, when we use a change of variable in Laplace transformation actually will do what? Will transfer the time signal into the S domain signal. Now the S domain signal is, or the S domain is not actual domain. It's virtual domain. But simply why I go there? Because there the differential equation will be transferred to algebraical equation. And we know that dealing with algebraic equation is more straightforward than solving or dealing with the differential equation. Here are the same. If you notice that when we find the torque, here simply the voltage equation is decomposed such that I'm having meaning for each term. For example, the first one actually is what? Is the drop voltage across the resistance. The second term is what here? This is an induced voltage due to rotation. The third term here is what? This is actually an induced voltage due to static coupling. The same thing for the rotor circuit. I'm having now meaning. I can understand each term, the contribution of each term to the power, let's say. When I multiply by the current, I know the first term will generate the losses, the power losses. The second term here, which is associated with omega, this one will contribute in the developed power or the mechanical power or the converted power. And the last term, which is the current multiplied by d by dt of lambda, actually this has a relation with the energy stored in the magnetic field. So from here, I can find an expression for the torque without going to a very, let's say, complicated mathematical calculation. Here, simply in 1 or 2 steps, I can get an expression for the torque from my understanding or our understanding of the voltage equation in the QD reference frame. This is in the first stage. The second stage, if you noticed, in the ABC reference frame or in the machine variable reference frame, the inductance, which is the LSR, or the mutual inductance between the stator and the rotor, was a function of theta r. So it's a function of time. So it's time varying. So this will make the system time varying. But when we use the transformation, then the system or the matrices is now constant, only a function of geometry. And this is also another advantage of the reference frame theory. Understood? Good.
يس دكتور معلش كمان بس ترجع
تفضل.
الرسمة اللي رسمتها من شوي اللي هي الاي بي سي والكيو دي مع بعض. ايوه دكتور الكيو دي هون شو في ستيشنري وفي روتيشن. كيف معلش ترسم الروتيشن بالنسبة للكيو ستيشنري على نفس الرسمة؟
Okay. Now, either you are missing my point or I cannot understand you. Now, the Q and the D is arbitrary or virtual, yeah?
Yes.
Does not exist in physics, let's say, yeah?
Yes.
Although they are existing in certain machines, such as the DC machine, I'm having the quadrilateral axe and the direct axe, but simply here in the three-phase system, I'm generating a reference frame. Now, the reference frame can be set anywhere. So let's assume this is the A. Let's assume this is the B. Let's assume this is the C. Now, the reference frame is introduced by who? By me, by you. Yeah? Yes. I will introduce a reference frame. So someone will say, I will put Q here. Or someone will say, no, put Q here. Or someone will say, no, put Q here. Or someone say, no, put Q elegant to the A. Yeah? So if I decide the Q, automatically I decide the D, yes or no? Why? Because the D is 90 degrees behind the Q. Yes? Yeah? Yes. Okay. What information here I know? I know the speed that the reference frame is rotating. Yes? Because either I will fix the frame, which means that now the frame is stationary, or I'm allowing the frame to rotate by sequence speed. Yes? So the only thing that I don't know is what? The initial angle. Yes? Yes. Which means that I don't know, should I put it here? Or should I put it here or start here? Yes? This is called what? Initial angle. Do you remember when I say this is what? I think all of you say that this is theta r, which is the integration of omega r d tau plus theta r of 0. This one is the initial angle. The same thing, if I'm asking you what this one, and I'm assuming here arbitrary reference frame, you are telling me this is theta, which equals the integration of omega d tau plus theta of 0. This one is what? The initial. Good. Now, if I'm attaching the frame, I will put the frame in anywhere. Yeah, in anywhere. Yes, because I'm attaching the frame, so I can put it anywhere in the space. Now, physically, can I put it anywhere? No, because I don't know exactly where is the rotor position or where is the rotor flux. Let's say, yeah? If I need to elegant the reference frame with the rotor flux, I don't know actually where is the rotor flux. But simply, I need in the second stage, I need a controller in order to what? In order to make sure that I'm matching the frame. For example, do you remember say that in the in the transformation, we are using scaling factor, which was 3/2, for example. Do you remember this one?
Yes.
Okay. Now, this one actually is correct if I'm having balanced system. And if I'm transforming and there's no initial condition, there's no initial angle, then in the end of the day, VQ will equal to what? VM. Yeah? And VD will equal to what? 0. Yes or no? Yeah?
Yes.
So simply someone will say, I can regulate VD to equal to 0. If this correct, then simply this means that now the reference frame is attached to the direction that I needed. Yes?
Yes.
And understood?
Yes.
Good. Do you have any question?
Oh, thank you.
دكتور نفس الريفرنس فريم يعني كيو اس ودي اس نفسهم رح يكونوا بس بالنسبة برضه للروتر.
Now simply I can use a reference frame which is attached to the stator, and I can refer the stator quantity and the rotor quantity to that frame. Yeah, correct? Or I can assume in the end of the day, if you notice, when we referred the rotor, we say that this is AS. We say that this is AR. We say that this is the BR, and we say that this is the CR. And here I'm capturing certain time because this rotor is rotating. The rotor is rotating, so AR, BR, and CR are changing their placing. They are rotating. So I'm freezing the time in order to plot. I'm freezing the time, and this one is theta. Now after that, I'm having a reference frame. This reference frame can be here, for example. This is the Q, and this is the D. Yeah. Now this reference frame, from here to here is the angle between the stator and the reference frame. Yeah.
صحيح.
Yes. And from here to here, this is the angle between what and what?
The rotor and the reference frame.
So simply, if I need to find KS, it will depend on which angle in theta, correct? Yeah. If I need to find KR, it will depend on which theta. And we call it beta. Remember, theta minus theta R. Yeah.
Yeah.
Good. Okay. And in the end of the day, I need to attach the frame. I need to elegant the Q or the D in certain direction in order to achieve something. In order to what? To achieve something. And this is, by the way, very good in order to pave the way for the vector control. Because in the field-oriented vector control, I'm having meaning for the reference frame. I'm attaching the reference frame, for example, such that the d-axis of the reference frame is pointing toward the rotor flux. And let's see what advantage I can get from there. So let's start with the field-oriented control of induction machine, or what we call vector control of the induction machine. So let's start with the field oriented. Please, if you have any question, ask. Control, or sometimes we call it vector control. Of the three-phase induction machine, symmetrical induction machine. Now, let's see. Let's assume that we'll start with the stator axis here. Let's assume this is the AS. and let's assume this is the BS, and let's assume this is the CS. And the same thing here, let's assume this is the AR. And let's assume that this is the BR. And in the same fashion, let's assume that this is the CR. And we know that the rotor is rotating by which speed? By omega r speed. Yeah. So the angle between here and here is theta r. Yes. Good. Now, in general, the rotor flux will be generated. And let's assume the rotor flux is pointing toward anywhere. Let's assume that the rotor flux is pointing here. This is lambda r. And let's assume for simplicity, so lambda r by definition is the rotor flux. And let's assume, for simplicity of the discussion, let's assume lambda r by assumption to be constant. Yes, now we know that the flux is rotating by which speed? Lambda r is rotating by which speed?
Synchronous.
The synchronous speed, yes. So the flux is rotating by what? By the synchronous speed. So this one is rotating by omega e, and omega e is the synchronous speed. So now I will attach my reference frame. Let's assume that I'm lucky such that I will attach a reference frame such that the dx is pointing toward the rotor flux. So let's assume that this is my DE, and 90 degree ahead of that, I'm having the QE, and now this reference frame is rotating by omega e. Yes, until here, understood my assumption? I'm assuming that I'm having a reference frame, and I managed to put the D of the reference frame in the direction of what? Of the rotor flux. Yes. Later on, we will discuss how we can do that. Yeah. Do you remember the initial condition? The initial condition I don't know, by the way, huh? Because I can't.
زي وكأنه عملنا assume إنه QD reference هما بالsynchronous speed.
Q and the E is rotating by synchronous speed. But also I'm assuming something else. I'm assuming that my dx is pointing toward where? Toward the flux. Yes. I'm assuming that my dx is pointing where? Toward the rotor flux. And it's rotate with the same speed. Yes. Now, in general, you know that lambda r as a vector should be decomposed in two components. Yeah. Which is the lambda dr as a vector plus lambda qr as a vector. Yes? Correct? Yep.
Yes.
Okay. Now, due to my assumption that all the rotor flux is pointing toward where? Toward the d-axis. So simply this means that lambda QR is equal to what?
0.
0. Yes or no? Now see, if this is the D and this is the Q, and if this is the rotor flux, then lambda R has two components. One is lambda DR, and one is what? Is lambda QR, yes? Now, if I manage to put, this is the D, this is the Q, and now here is my flux, lambda R. Then simply here, from here, I can get what? Lambda DRE is equal to lambda R, and lambda QRE is equal to 0. Yes or no? Huh?
صحيح. مظبوط.
Good. And also I need you to remember that in synchronous rotating reference frame, all the sinusoidal signal is seen as a constant. Yeah. So here I will write or recall for you. In the synchronous rotating reference frame, the sinusoidal function is seen as a constant. And let's start writing the equation, the rotor voltage equation, in the synchronous rotating reference frame. And for that, let's start with the d-axis, the voltage equation in the d-axis. So here is the vector control equation. And here I'm assuming that lambda R is constant. And I'm assuming that I managed to put lambda R in the direction of what? Lambda DRE, or lambda DRE, which is rotating by the synchronous reference frame, is equal to lambda R. Yeah, so let's recall the voltage equation, VDRE. Now this E indicates that I'm using the synchronous rotating reference frame. This is indication of the used reference frame. So E stands for the synchronous rotating reference frame. So VDR will equal to RRIDRE plus D by dt lambda DRE, and also here we have the minus omega E minus omega R lambda QRE. Now I'm forgetting the dash dash dash, all the quantities refer to the stator, but because I'm having E, I will not write also a dash. Now let's see. Due to our assumption, let's assume also I'm interested in the squirrel cage induction machine. So in this case, VDR E is equal VQRE will equal to 0, which means that either I'm shorting the terminals or I'm using the or I'm assuming that my machine is a squirrel cage machine. Now, due to my assumption that all the rotor flux is pointing toward the direct axe, or later on we call it the magnetic axe or the field axe, then lambda QRE is equal to what? Equal to 0, correct? Yes.
صحيح.
Yeah. And due to my assumption that lambda R is constant, if I differentiate a constant, this will equal to what?
0.
So this is also will equal to 0. Now, due to my assumption of short circuit or squirrel cage, VDR is equal to what? 0. So simply from here, I can conclude I DRE will equal to what? 0. Correct? Yeah. Now, if we go to see the Q axe voltage equation, and if we write it, VQRE will equal to RRIQRE plus omega E minus omega R lambda DRE plus d by dt of lambda QRE. Now let's see. This term is equal to what? To 0. By assumption, all the flux is pointing toward what? The D. Correct? And VQR is equal to what? 0 due to what assumption? Either short circuit in the rotor or squirrel cage. Huh? Even if I'm having one rotor, I'm shorting the terminals, or I'm using a squirrel cage induction machine. So now, simply, I can find a relation between the relative speed or the slip speed, let's say. This actually is omega slip, the slip speed. So I can find a relation omega slip will equal to minus RRIQRE over lambda DRE. Yes? Good? Until here?
Yes.
Good. Now, what else I need in order to continue? I need to find the slip speed in terms of something that I can calculate. Remember, in general, the rotor current or the quantity in the rotor is hard to be measured or impossible to be measured. For example, can I measure the current in the squirrel cage? I cannot measure the current in the squirrel cage because the squirrel cage by itself is what? Is a solid, is actually bars shorted by what? By a rings. So I need to rewrite the slip speed in something that I can measure, which is actually the stator quantity, So now, if we recall the flux linkage, lambda QRE was equal to LLR IQRE plus LM IQRE plus IQSE. Now, if I collect the terms here, and now by assumption, lambda QRE is equal to 0. So here I can say LLR plus LM all multiplied by IQRE plus LM multiplied by IQSE, and this actually is the LR, yeah, the rotor inductance. Yes. So from here, if I solve this equation with respect to IQRE, I will get what? IQRE is equal to what? Who can help me with that?
Minus LM IQSE over LR.
Yeah, thank you. So instead of IQRE, I can write instead of that minus LM over LR IQS, correct? Yeah. And instead of lambda DRE in the same fashion, lambda DRE, I can write it to be LR IDRE plus LM IDSE. Now remember, this one was equal to 0 from the first equation. So this will end up to be lambda DRE to equal LM IDSE. Now omega slip, if we remember, it was what? Omega slip, if we recall, it was minus R IQR lambda DR. So minus RR IQRE over lambda DRE. Now let's substitute instead of IQR by minus LM over LR IQFS. So this one will come here, and lambda DRE to be substituted by LM IDS. So this one will come here. Now, if I do so, I will end up with omega slip equal to R over L R IQ SE over IDS. Now, in general, you know that L over R is equal to what? In the transit response.
Lead time constant.
It's the time constant. Yeah, it's the time constant. So this is what?
1 over tau.
Yeah, 1 over. So simply this will equal 1 over tau. Which tau? Tau of the rotor. Yeah, because this is R of the rotor, L of the rotor, multiplied by IQSE over IDSE. Yeah, good. Yes. So now this is the omega slip. We have a relation now between the slip speed and the stator current, which is the Q component of the stator current and the D component of the stator current. Good. Yeah. So now let's recall the torque. If we recall the torque to see what's advantage I can get when I'm elegant the rotor flux to be pointing toward the D-axis of my synchronous reference frame. Now the torque was equal, TE was equal 3 over 2 P over 2 LM IQ SE IDRE minus IDSE IQRE. Now simply we know that lambda DRE is equal LR IDRE plus LM IDSE. So from here we can find IDRE if I need to substitute, it will be lambda DRE minus LM IDSE over LR. The same thing I can have for the IQRE, which actually equal lambda QRE minus LM IQSE over LR. Now, if I take the first one here, substitute it here, and the second current here, substitute it here, and simplify, I will get the following expression for the torque. So TE will equal to 3 over 2 P over 2 LM over LR IQSE lambda DRE minus IDSE lambda QRE. And this is very interesting, by the way. Now, this term equal to what? 0. Why? Due to our assumption, due to our assumption that all the flux is pointing toward the D. So simply this means that under vector control, under field oriented vector control, actually the rotor field oriented vector control, TE will equal to 3 over 2 B over 2 LM over LR, and I will end up IQSE lambda DRE. Now, do you remember lambda DRE under the vector control equal to what? Lambda DRE under the vector control equal to what?
LM IDSE.
Yes, thank you. LM IDSE. So let's substitute this one here. We are getting a very, very, very interesting formula. 3 over 2 P over 2. Now LM square over LR, and I will get IQSE IDSE. Now, see, those are constant, yes or no?
Yes.
Yeah. So simply this means that the torque is proportional with IQSE and IDSE, yes or no?
Yes.
And I have another interesting formula, which is lambda DRE, which equal lambda R equal LM IDSE. Yeah? Correct? Yes? Yeah? So simply this means that the DX current, the stator direct ax current, or the is what? Contributing in the flux or the torque?
Flux.
Huh? IDS contribute to what?
التورك.
كيف torque? IDS. If I multiply it by a constant, I will get what? I will get what? The flux. So simply this means that IDS is the flux component of the current, or the field component of the stator current. So IDS is what? Is the field component of the stator current. If IDS is the field component of the stator current, then IQS is what? If this one, yeah, this will be what? IQS will be what? The torque component of the stator current. Yeah, and this is very interesting. Why? Because now I can understand what I should control. If I need to maintain the rotor flux to be constant, I need the stator, the field component of the stator current, or IDS, to be constant or regulated to be constant. If I need the control, the torque, then I will control what? The torque component of the stator current, which is the IQSE. And this is very interesting because this will make the induction machine control as easy as controlling of a separately excited, full compensated or full compensated from the armature reaction DC machine, actually. And this is very, very, very interesting. Good. Until here. Do you have any question until here? Do you have any question until here? So this is also another advantage of the vector control. Do you see our selection of the vector control? Our selection of the vector control will make the controlling of the machine very simple, such that I can understand which component I should control to control the flux, for example. I need to control the IDS, the field component of the stator current. I need to control IQS in order to control the torque. If I control the torque, I will control the speed. Yeah. Yes. So now the question, what about if I'm having a phase difference in the initial phase, in the phase stage? I cannot I'm not that lucky to put my reference frame in the direction of the rotor flux. Yeah. What I can do, I can assign it in space anywhere, and I can rotate it in synchronous speed. Yes, this I can do that. But can I make sure that my selection is 100% perfect? No, of course I cannot. So what I need a controller in order to make this assumption valid, or I need a controller in order to, even if my selection or initial selection is not correct, this is lambda r, and let's assume this is my initial selection, DRE. I need a controller such that in the end of the day, my dx of the reference frame is attached to the rotor flux, and this is actually can be done using the control theory. Yeah. And simply let's discuss the vector control block diagram. And here I will discuss with you the indirect vector control, in which theta E, because in the end of the day I need to do transformation, so I need to find the angle, and this angle is theta E, and E here referred to the synchronous reference frame. And in order to do so, if I need to realize the vector control, you know that all of our calculation is based on the reference frame. So simply, actually here I'm having what? Let's assume here I'm having the ABC. Let's assume that here I'm having IA. IB, IC, in order to find the IQ, E, and the IDE. Here I need a transformation which based on theta E, the synchronous rotating reference frame, and this will be A, B, C to QD transformation. In the same thing, if I know the reference current for the stator, the torque component, and the feed component, and I need to do, let's say, a current controller, either hysteresis or PI plus pulse modulated controller. I need to generate, for example, for the hysteresis, I need to generate the reference current in the actual coordinate, which is the ABC coordinate. So here also I need to do my transformation, I need the angle theta E, and here I will do transformation from QD to the ABC. So here I need, in order to realize the vector control, I need to construct theta E. And you know that if I need to find theta E, then theta E is nothing more than the integration of omega E d tau. And this will be the integration of omega E is nothing more than omega slip plus omega R d tau. If I calculate theta E in this direction or this way, this actually is called the indirect vector control. Where theta E is evaluated indirectly. Here theta E is evaluated indirectly. And simply omega slip, if omega R, I can measure it, this one, to be measured. Using tacho generator, using encoder, I can calculate the theta. And omega slip, this one, I will calculate. Under the vector control, it was 1 over tau R IQ SE over ID SE. Yeah. So now let's discuss the speed control under the indirect vector control. So for that, let's start from reference speed. Let's assume this is omega R star. And if I need to do speed controlling, I will compare the reference with the actual omega R. Here an error will go through a speed controller, and in general it's actually a PI control. So this is a PI speed controller. And let's assume that this one with anti-wind up, anti-wind down, in order not to saturate. So this will, let's say, specify the maximum value and the minimum value. Now, the output of the speed control in general is the torque. So this will be the TE star. The actual of the, or the output of the speed control is actually the torque command. Now, the torque command, remember, under the vector control, the torque was equal to what? The torque was equal 3 over 2 P over 2 Lm square over Lr multiply IQS star IDS star. So this one is constant. Yeah. So this one is constant. Let's assume this one is called KT. So this will be IDS star IQS star. So if I'm having the torque and I need this Q1 of this IQS star, and here it's all in the synchronous rotating reference frame. So if I need to generate the reference current from the reference torque, the first thing I need to scale it by 1 over KT. So here I'll multiply by 1 over KT. Then I will divide by and this will be the N. So I'm dividing here by the IDS star, the reference current of the field component of the stator current. So what I will get here?
IQS.
Yeah, I will getting the, let's say, the torque component of the stator current. So IQS star in the synchronous rotating reference frame. Now, if I'm having the IDS and the IQS, I can do the transformation. Of course, if I'm having theta. So here I need to do the QD to the ABC reference frame. And this in general will generate to me IA star, IB star, IC star. So here I need the theta E. Now, how to calculate the theta E? We said that we will use the indirect method. So the first thing I will calculate omega slip, and remember, omega slip was equal to what under the vector control? 1 over tau R, yeah, I Q SE over I DSE, yeah? Yes. So simply now this is the IQS and this is the IQ, the IDS, and this is the IQS. Pick this one here and this one here. And those, let's go to a block. And in this block, I will evaluate 1 over tau R, IQ SE over ID SE. Now I will calculate here what? Omega slip, omega slip. Now this omega slip, if I add it to omega R, what I will get?
After the integration, we get that.
I will go to omega, yeah? Now if I integrate, I will get what? Theta, yeah? I will get theta E. So I will get here theta E. Yes? Now omega R, I will get it from where? From the machine. So let's assume here I'm having my machine, and I'm using tacho generator, let's say, in order to measure the speed. And remember, this will give me indication for the mechanical. So I will multiply it by P over 2 in order to convert to electrical. So this will be theta Rm. Now this will be here theta R. This will be a link here, and this will be a link here. Yeah. Now the machine is fitted by three-phase system. Yeah. And in general here, I need a converter in order to regulate the voltage. So let's assume this is IGBT base converter, three-phase system, 3-leg inverter. And here I'm having the DC link, let's say, plus minus. Either I'm having a pure DC or as a result of a stage of rectification. Now the inverter here need gate pulses. I need a gate pulses, 6 for the 6 switches, 3, and the 3 is complement. Those are gate pulses. And here let's assume this is the current control and the gate drive. So for the current control, I need to feed back the current. So let's assume that this is the IA. Now this one, let's assume it is the IB. And this one here is the IC. Although if this one is balanced, I can use 2 current and generate the third one such that IA plus IB plus IC is equal to 0. So this can be seen as a reduction in cost if I reduce the current transducer. Now this is the inverter, voltage source inverter. And now the only block that I need to discuss is the current control. Yeah, do you have any question until here?
دكتور هسا بالبي اي كنترولر كيف بقدر يحول الأوميجا لتورك؟ يعني مش هو كنا ناخذ بالبكالوريوس إنه بيحول الإيرور للستيد ستيت لزيرو وظيفته؟
Now, the BI control, the ultimate objective of any control system is to make the error go to 0 as t go to infinity. Yeah? Yes?
Yes.
Yeah. Now, simply, the output of the speed control is a torque. Why? Now, if you have a machine, and the machine, this one, this machine is connected to a mechanical system. So this is one TL, and in order to rotate the machine at certain speed, I need what? TE. And according to the swing equation, J d omega by dt must equal the summation of the torque. Yeah. So if I need to go from speed A to speed B, either I need to increase the torque if I'm going from lower speed to higher speed, or I need to reduce the torque if I need to deaccelerate. Yes or no?
Yes.
So simply this means that the output of the speed control will give a command either to increase the torque or to reduce the torque. Yes?
Oh.
So simply this means that there's a relation between the output of the speed control and the reference torque. Yes?
يعني عم بحاول أتخيل الموضوع بس إن شاء الله مش قادر أتخيل الموضوع. دكتور أنت معي؟
معك. Now if you are driving a car, and you are run at speed, let's say, n here because it's a linear. Let's assume 40 kilometer per hour, and you need to run at n equal 100 kilometer per hour. What you should do?
أزيد السرعة.
You will increase the speed. Of course, this is your target. Huh? Your target is to increase the speed. Yes? So how to increase the speed? You need to increase the force, correct? Yes or no?
Oh, yes.
Yes? So simply, if you have a control, if you have a speed control, which virtually you have in your brain, by the way, because this is the, oh, let's say this is n, because here I'm having linear. This is the n star, and this is the n, and this will be E of n, and then you have a BI count controller, and this BI count control will give you reference force. You will translate later on to what? To the opening of the fuel valve, or let's say the pressing or the pressing on the fuel pedal, correct?
Yes.
Yeah.
ما سمعت إيش حكيت.
So simply here, if you need to increase the speed, this means that you need to control the gate of the fuel injection. Yes.
Yes.
And how you can control this one? By controlling the pressing and depressing of the fuel pedal, correct? The fuel pedal. If you press it down, this will what? Speed up the car or reduce speeding of the car?
راح يزيد.
And if you release your leg, so simply this is controlling the gate, right? So in the end of the day, this will control what?
تمام.
The force, correct? Actually, you are controlling the force in order to control the torque. Sorry, in order to control the speed. Yeah. Okay. So, do you have any question? Do you have any question here until here? So I need to discuss with you the current controller now. Now in the current controller, we have two methods. The first one is the hysteresis current control.
دكتور عادي نخليها للمحاضرة الجاية، إنه والله بطلنا نركز.
خلصنا احنا المحاضرة يعني؟
خلصت المفروض.
يا ريت لو للمحاضرة الجاي.
The hysteresis current control. Okay. طيب. See you next lecture إن شاء الله. السلام عليكم.
يعطيك العافية.
الله